This video is going to be about Abelian groups and cyclic groups, which are special kinds of group. And we're going to begin by defining an Abelian group. And to do that, I need to talk about what it means for two elements of any group to commute. So if you have two elements, lowercase g and lowercase h, of a group G star, then we say those things commute if G star h and h star g are equal. So for example, if we work in the group of integers under addition, well, if you look at 2 plus 3 and 3 plus 2, those things are of course equal to one another. And in fact, every two elements in the group of integers under addition are going to commute with one another. So on the other hand, if we work in the symmetric group, so if we look in S3, for example, if we look at the permutations 1, 2 and 2, 3, so here the group operation is composition, as is usual. I'm not going to write down the actual group operation. I'm just going to write these side by side to indicate that we combine them using the group operation. And what we get when we do this is we get the permutation 1, 2, 3. But on the other hand, if we do this the other way around, so 2, 3, 1, 2, like this, this time we will get 1, 3, 2. Okay, those two permutations, 1, 2, 3 and 1, 3, 2 are not equal to one another. So that's telling us that these two elements, 1, 2 and 2, 3 of the symmetric group S3, they don't commute with one another. Okay. We then make the definition that a group is called abelian or commutative if every two elements in that group commute with one another. So let's see some examples of commutative and non-commutative groups. So first, these two examples which we've now just seen. So first of all, if we take the group of integers under addition, z plus is commutative. So the group operation is ordinary integer addition, and you know ordinary integer addition is commutative. So similarly, if we look at the group of integers modulo n under addition, of course that will also be commutative. And if we look, for example, at zp cross under multiplication, so remember that means the set of all non-zero equivalence classes under congruence modulo p, where p is a prime number and the group operation is multiplication. Well, again, this will be commutative simply because ordinary integer multiplication is also commutative. Let's now look at the other example that we've just seen above. So if we take S3, so the group operation here is composition of functions, this thing is not commutative, not abelian. The reason for that is being commutative requires that every two elements commute. But on the other hand, we've seen an example of two elements of S3 which don't commute. So for example, 1, 2 and 2, 3 do not commute. And of course the same example shows that Sn is not commutative whenever n is greater than or equal to 3. So for the same reason, Sn under composition is not commutative for n greater than or equal to 3. On the other hand, if you look at S2, well, S2, the permutations of two things, it's only got two elements. So there's a transposition 1, 2, and there's the identity element E or ID, whatever you want to call it. This thing is commutative because if you check the elements, the only possible compositions you've got are E composed with 1, 2, and 1, 2 composed with 1, 2, and E composed with E, and all of these things commute. So this thing is commutative. Okay, let's have one last example of a non-commutative group. Let's say we look at the group of n by n matrices under matrix multiplication. So G, L, N, let's say C. So the group of all n by n complex numbers, n by n matrices consisting of complex numbers entries. This is not commutative, so long as n is greater than 2. Okay, if you take any two n by n matrices for n greater than or equal to 2, then the chances are those matrices don't commute with one another. And so it's easy to produce a counterexample showing that this group is not commutative. So there's nothing special about the complex numbers here. So similarly, G, L, N, R, the group of all n by n matrices, n by n invertible matrices with real entries, is also not commutative, so long as n is greater than or equal to 2. On the other hand, if you want to think about what happens when n is equal to 1, well, GL1 of C is, let's put this in inverted commas, it's the group we've met before. It is the group of all non-zero complex numbers under multiplication. So this thing is commutative because complex number multiplication is commutative. So this is Abelian commutative. Those things mean the same thing. And similarly, GL1 of R is the group of non-zero real numbers under multiplication. And of course that is Abelian because ordinary real number multiplication is Abelian. Okay, we now have another special class of cyclic groups, of groups called cyclic groups. And here's the definition of a cyclic group. A group G is called cyclic if it's equal to the cyclic subgroup generated by one of its elements. So I've copied for you at the bottom there the definition of pointy brackets G, the cyclic subgroup generated by G. You'll remember from our previous lecture that it's just the set of all powers of G. So that's what it means for a group to be cyclic. It's cyclic when it's equal to one of the to the cyclic subgroup generated by one of its elements, and an element little g such that G is equal to the cyclic subgroup generated by G is called a generator of G. So in a cyclic group it has at least one generator, but if you look at a general element, maybe it is a generator, maybe it isn't. So some elements will be generators and some elements will not be generators. So let's look at some examples of cyclic groups. We're going to begin our examples first of all with the group of integers under addition. So the group of integers under addition is a cyclic group. So Z is cyclic. So the reason for that is that if you look at the subgroup generated by 1, well, what that means is the cyclic subgroup generated by 1, that's all the things you can get by combining 1 with itself and combining the inverse of 1 with itself using the group operation. But you can get any integer by adding up 1 some certain number of times or adding up minus 1 some certain number of times. So that means the cyclic subgroup generated by 1 is equal to Z. So there is an element of Z where the cyclic subgroup generated by that element is the whole group, and that means Z is cyclic. So the next question to ask would be which elements of Z are generators. We found one generator, namely 1, but are there any other generators? Well, yes, there are. If you take the subgroup generated by -1, then again you can get any integer by adding -1 to itself a certain number of times, or by adding the inverse of -1, which is 1, to itself some number of times. So -1 is also a generator. So these, in fact, are the only generators. The reason that these are the only generators is if you think about the cyclic subgroup generated by some integer a, well, that is the set of all powers of A in our group theoretical sense, so the set of all things which you can get by combining A or -A with itself using our group operation, which is addition. So what you can get is all the multiples of A. So we might write that as NA for n in Z. And if A is not 1 or -1, then there are integers which are not multiples of A. So this thing, well, this is all multiples, all integer multiples of A. And if A is not plus or -1, then there are integers which are not multiples of A. So anything not divisible by A certainly isn't a multiple of A. So this is not going to be the whole of Z if A is not plus or -1. We actually had some notation for this which we used before, this cyclic subgroup generated by A, but previously we wrote this as A times Z. So we looked at the subgroup 2Z of Z, and we observed before that that actually was the cyclic subgroup generated by 2. Alright, so Z is a cyclic group, but not all of its elements are generators. In fact, it only has two generators, plus or -1. Okay, example 2, let's look at the integers modulo n under addition, so Zn plus. Again, this is cyclic. So so the class of 1 modulo n is a generator. And again, this is it's clear that you can get every element of Zn by adding up 1 enough times, by combining 1 with itself using the group operation, because the elements of Zn are the class of 0, class of 1, class of 2, up to the class of n minus 1. And you can get those you can get the class of I by adding 1 to itself I times. So the cyclic subgroup generated by 1 really is the whole of Zn, and that means Zn is cyclic and 1 is a generator. And there may be other generators as well. You can experiment with adding numbers to themselves multiple times, and you can see whether a particular element is a generator of Zn or not. And in general, some of the elements will be generators and some of them won't be. Okay, let's look at another example. Let's look at S2, the symmetric group consisting of all permutations of the set 1, 2. That thing is cyclic. Because if you look at the cyclic subgroup generated by 1, 2, so all the powers of the permutation 1, 2, well, 1, 2 to the 0 is the identity, 1, 2 to the 1 is 1, 2. That exhausts all the elements of S2, so this thing is S2. So 1, 2 is a generator of S2, and S2 is cyclic. But on the other hand, if you look at S3, or actually if you look at any symmetric group Sn for n at least 3, this thing is not cyclic. So we're going to see an easy necessary condition for a group to be cyclic later on, which would immediately tell you that S3 was non-cyclic. But if you want to check this now, you could just look at all the generators of S3, all the elements of S3, sorry, and you can see easily that they're not generators of S3. So S3 is an example of a group which is not cyclic, and we'll come back to exactly why that is later on. All right, let's move on for this necessary condition for a group to be cyclic. which is that a cyclic group must be abelian. Let's explore why this is true then. So here is a lemma which says cyclic groups are abelian, and let's try and prove this lemma. Okay, let's let G be a cyclic group, and if it's a cyclic group then it has a generator, an element where the cyclic subgroup generated by that element is the whole group. So if we've got a cyclic group, then it contains at least one generator, and we're going to write little g for a generator of that cyclic group. So if this is cyclic, then any two elements of my group G, they're in this cyclic subgroup generated by little g, so they're equal to powers of G. Alright, any two elements in the group are equal to powers of our generator, so g to the I and g to the j for some integers I and j. And now we're just going to use the exponent laws to see that these things actually do commute with one another. So if we look at g to the I combined with g to the j, well, the exponent laws tell me this is the same as g to the power I plus j. On the other hand, I plus j, that's the same as j plus I. So we've got g to the j plus I, and this, again using the exponent laws, that's g to the j times g to the I. Okay, so our conclusion is that if you take any two elements of G, then those things are equal to g to the I and g to the j for some I and j, and g to the I times g to the j and g to the j times g to the I are equal to one another, because they're both equal to g to the power I plus j. So we've shown that any two elements of our cyclic group G commute with one another, and that means our group is abelian. Alright, so we have a necessary condition for a group to be cyclic. If a group is cyclic, then it must be abelian. And that allows us to say that certain groups are automatically not cyclic. They can't be cyclic because they're not abelian. So we can apply this to Sn is not cyclic if n is greater than or equal to 3, because we know that it's not abelian. So if it's not abelian, it can't possibly be a cyclic. And similarly, GLN R, the group of n by n real matrices under matrix multiplication, is not cyclic if n is greater than or equal to 2 this time, and also GLN of C. For the same reason, it's not abelian, so it can't possibly be cyclic. Okay, if a group is cyclic, it's got to be abelian, so it's natural to ask, well, does it work the other way around? If a group is abelian, does it have to be cyclic? And the answer is no, abelian groups don't have to be cyclic. So let's look at some examples of abelian groups which are not cyclic. So examples of abelian groups which are not cyclic. Okay, example 1. Let's look at the following subgroup of S4. So I'm going to take H to be equal to this set, the identity, let's call it ID this time, the permutation 1, 2, the permutation 3, 4, and the permutation 1, 2, 3, 4. So a product of 2 disjoint 2 cycles. So you can check that this thing is a subgroup of S4, and it's good practice for you to do that. So pause this video and check the subgroup definition for this, for H. Okay, I hope you did that. Let's now check that this thing is not cyclic. So I'm claiming this is not a cyclic group. Well, to be cyclic, you have to have the property that one of your elements is a generator. So it would have to be the case that the cyclic subgroup generated by one of these elements was equal to all of H. So to check that that's not the case, we're just going to look at each of the cyclic subgroups generated by an element of H in turn. So if I look at the cyclic subgroup generated by the identity, well, powers of the identity only give me the identity. So this is equal to just the identity, and that's not all of H. Okay, so the identity is not a generator. Let's look at some more elements, some more cyclic subgroup generated by elements of H. Okay, let's look, for example, at the cyclic subgroup generated by 3, 4. Okay, well, I mean, I could work out what the elements in here, and it's actually easy for me to do it, because if you look at the powers of 3, 4, 3, 4 to the 0 is the identity, 3, 4 to the 1 is 3, 4, 3, 4 squared is the identity again, you can check that, 3, 4 cubed is 3, 4 again, and so on. So the only things you get in there are the identity and 3, 4. So actually I was writing the identity as ID, wasn't I? 3, 4, and those are the only things you get, so that's not all of H. Okay, but there really is a smarter way here, isn't there? Because, I mean, we actually know the size of a cyclic subgroup. We know that the size of the cyclic subgroup generated by an element X is the order of X. So you could notice in H that all of the elements in here actually have order 1 or 2. So in fact, every element of H has order 1 or 2. So every cyclic subgroup generated by an element of H has order 1 or 2 as well, because we showed in our last lecture the order of the cyclic subgroup generated by an element is equal to the order of that element. But H has order 4, so we can't have any cyclic subgroup of H being equal to H, because cyclic subgroups have got order, size 1 or 2, whereas H has got size 4. Okay, there's our example then of an abelian group H, which you have to check that it's abelian. It's not obvious. You need to compute those products in each order, but you can check that H is abelian, and we've now shown that it's not cyclic. Okay, let's look at another example. So example 2, we're going to look at a group of matrices. So I'm going to define V to be equal to the following set of matrices. So V consists of the 2 by 2 identity matrix, this matrix 1, 0, 0, minus 1, this matrix minus 1, 0, 0, 1, and finally minus 1, 0, 0, minus 1. Okay, I claim that that is a subgroup of GL2R, and you need to check this. It's not obvious that it's a subgroup, so you need to do some work to check that. You need to check that it contains the identity. Well, that's obvious. You need to check that it's closed under taking inverses. Well, you have a formula for the inverse of a 2 by 2 matrix, so you can just directly check that the inverse of each element of V is in V again, and you need to check it's closed under products, so you need to see what happens when you multiply together any 2 elements of V. So an easy way to do that would be to draw up the group table for V and check that you really have the property that when you multiply two elements of V, you really do get an element of V. And the nice thing about drawing up the group table is you'll be able to see from the group table that this is actually an abelian group, that every two elements commute. And being abelian is actually reflected in a nice way in the group table. So if you think about the way we define the group table, you'll see that a group is abelian, at least a group is abelian if and only if it's actually symmetrical in its leading diagonal of its group table. Anyway, let's suppose that we've checked that V is a group and it's an abelian group. Well then again, for exactly the same reason as H, this is not cyclic. So V is abelian, but it's not cyclic. And as I say, this is for precisely the same reason as H. You can check that every element of V has order 1 or 2, so every cyclic subgroup of V has size 1 or 2. And if those cyclic subgroups have size 1 or 2, they can't be equal to all of V. And that means V cannot be cyclic, because being cyclic means you contain an element whose cyclic subgroup is the whole of U. Alright, let's look at one final example which is not quite so obvious. So I'm going to leave it to you to actually figure out why this is the case. So here is my problem. I claim that the abelian group R cross under multiplication and the abelian group R plus are not cyclic. Okay, so you should try and think of a reason why this is true. Why is it the case that if you look at the cyclic subgroup generated by an element of the non-zero real numbers, that can't be all the real non-zero real numbers? And why is it that if you look at the cyclic subgroup generated by a real number under addition, then that can't be all the real numbers? Anyway, that's something that's worth thinking about. Alright, we're now going to look at a way of writing down a cyclic group of a given order, so constructing a cyclic group of any finite order. So we're just going to worry about finite cyclic groups on this slide. We've already seen actually an example of infinite cyclic groups, because we've seen the example that the integers under addition are cyclic. So there's some standard notation and a standard construction that gives you a cyclic group of any given order, and here it is. We write Cn for the following set. So here is the set. It's E, a variable x squared, x cubed, up to x to the n minus 1. So this is supposed to be a set of size n. X is just some abstract variable. And we can make this into a group by defining a group operation on it. And the way we define our group operation is, well, we define x to the I times x to the j to be equal to x to the I plus j, except that we treat the exponents here as if they're integers modulo n. In other words, we replace I plus j here actually by its remainder on division by n. So where exponents are treated as if they were elements of the integers modulo n. So, well, what does that mean in practice? Let's look at an example. Let's take n equals 5, for example. So C5, as I've done it here, would be x squared, x cubed, x to the power 4. And if we do some calculations in this group, if I do x3 combined with x to the 4 under our group operation, we get x to the 7. And I'm treating these exponents as if they were elements of the integers modulo 5. So this is the same as x2 because 2 and 7 are congruent modulo 5. So we're replacing the exponents by their remainder when you divide by 5. So on the other hand, if I do something like, if I want to know the inverse of some of these group elements, so x cubed to the minus 1, that's x to the minus 3, and I can replace x to the minus 3 by its remainder when I divide by 5 if I want to see which element of this set it is. It's equal to x squared, like this. Okay, so there's an example of this this group, this construction for a cyclic group of a given order, and of course Cn is equal to the cyclic subgroup generated by x, because visibly every element of Cn is a power of x. So that means Cn genuinely is a cyclic group. Of course, it may have other generators as well, but at least x is a generator for Cn. Okay, so there's nothing special about the letter x as well, and often when we want to talk about two cyclic groups at the same time, we might use a different letter as a generator as well. So we'll also use different letters as generators. So if I want to work with two cyclic groups at the same time and I want to distinguish between their elements, we might write, for example, Cm to be e and y squared up to y to the m minus 1, just so I can tell the difference between the elements of my two groups. Okay, so that construction gives us a cyclic group of any given order. Alright, so the final thing we're going to do now is we're going to give a necessary and sufficient condition for a group to be cyclic, or at least for a finite group to be cyclic. And you're going to see that this condition really does only work when the group is finite, when it's got a finite number of distinct elements only. And that necessary and sufficient condition is that a finite group is cyclic if and only if it contains an element whose order is the size of G. So let's try and do this proof. So let's try and do this. Let's suppose first of all that G is a cyclic group, a finite cyclic group, and we're then going to prove that it actually must contain an element whose order is the size of our group G. So let's suppose, well, which direction are we doing? We're doing implies. Let's suppose that G is cyclic, and if it's cyclic it contains a generator. So let's have some notation for that generator. Let's say that lowercase g is a generator. Well, what can I say about the order of G? So I've copied for you down there at the bottom of the screen a lemma which we proved in our lecture about orders and powers, and that says that the size of the cyclic subgroup generated by an element lowercase g is equal to the order of G. So the order of lowercase g, that element G. So then the size of the cyclic subgroup generated by G is the order of G. We saw this before. But on the other hand, the size of the cyclic subgroup generated by G, our lowercase g here is the size of all of G, because the cyclic subgroup generated by G is the whole group. So the order of G, that's equal to the size of the subgroup generated by G, that is the whole of the group capital G. Okay, so we've shown that the order of any generator of our group capital G is actually must be equal to the size of G. So we've shown that capital G contains an element of order the size of capital G, and in fact any generator will have order equal to the size of our group. Right, let's do the other direction now. So on this in this direction, let's suppose that G is any finite group, and it contains an element whose order is the size of the group. So let's call that element little g, and let's suppose that the order of this little g is the size of the group. Okay, again, all we have to do is look at the size of the cyclic subgroup generated by little g. So then the size of the cyclic subgroup generated by little g, well, that's equal to the order of g. That's what the lemma that I copied at the bottom for you says. And by assumption, that's the size of the whole group. Okay, now this subgroup generated by lowercase g is a subset of g with size equal to the size of g. And this is where we use that g is finite. If you have a finite set and a subset whose size is the same as that finite set, the size of that finite set, well, that subset must be all of the set. So actually, in our case, the cyclic subgroup generated by g must be all of g. So this would not work if g was infinite, but it does work when g is finite. That means g is equal to the cyclic subgroup generated by one of its elements. So g is cyclic. Okay, we're done. We've done both directions of this result. So we've shown that it's true.